Okay, hello everyone. Our project title is Phase Alignment Estimation. And in order to do this phase alignment estimation, we need a lot of data to support. So we found a lot of data from the Imperial College London, and here are the list of the data set. For example, we have the 300W, which were published in 2013. And it has 68 marks and 600 samples. Also, we have the LFPW, which published in 2013, which has the 68 marks and 1,065 samples. And now let me introduce you our detection methodology. We have two neural layers. The first stage network is responsible for the initial detection of the approximate locations of 68 feature points from the images. The total number of the layers is 10, not including the polling layers. And the input layer size is 256 multiple 256 with 8 convolutional layers and 2 fully connected layers. After the detection of the first stage network, the phase pose is calculated based on the 68 detected feature points, and then the pose is corrected to be close to a positive phase. And then the corrected smaller images area contain 68 points is input to the second stage neural network. And then the second stage neural network is responsible for refining the detection results and outputting the final coordinates. This level, not counting the polling layers, have 6 layers and 28 multiple 28 input layers, 5 convolutional layers, and 2 fully connected layers. It should be noted that second level neural network has a large number of the neural networks, and each feature point corresponds to one neural network. And then we have some data set validations. Go through the data set to verify that an annotation cooperates with the image use OpenCV. And this picture is from the data set, which have already pointed by the data set. So we can use this data to train our model. And now is the data processing part. We need to do something on the data. So we cropping the image, and we have 220,000 faces extracted. We extracting them all of the faces from the data set, and we square shape, including all the key points of the face. And then we need to generate the TF record files, which can speed up the training process. We scaling the face exacted to 256 multiple 256 first, and then we compress the images to save the space. And then we convert the original key point coordinates. And then we divide our original data sets into 3 parts. The first part is the training part, which have the 200,000 data. And the second part and the third part is the validation and the test, which both of them have the 10,000 data. And this picture shows how the high resolution net works. The first stage consists of the high resolution convolutions, and the second stage repeats the 2 resolutions blocks. And the third stage repeats the 3 resolution blocks, and the fourth stage also repeats the 4 resolution blocks. And after our training, we have got a almost well done model, and we use this model to do something on our testing data set. And then we got these 5 we got some data which has already processed. And then this picture was some of them, and we can find that the face have already found and detected. And the next part is about the evaluation and the application.
Okay, so the first thing we need to point out is that during the training process we encounter some problems. That is, when the training step run to almost 120,000 steps, the loss function become very contain some errors. And so from the graph on the left side, we can see that the loss function is abnormal. So to solve this problem, we changed our loss function to mean square error, and finally our loss function the plot of our loss function become this. So we can see that the loss is gradually becoming small when the training step is going to be larger and larger. And after the training process, we run through 2,500 test files, and we got the following result. So here the NME means the normalized mean error. So here we got 25 for the normalized mean error, and the prediction was ran on RTX 2070 graphic card, and we got approximately 25 frame per second. And after getting the landmarks, we can calculate the post of a face from these landmarks. So with the landmarks coordinates, we can calculate the camera rotation matrix and the translation matrix respect to the screen. And using OpenCV2 library and some functions discovered by Rodriguez, we can solve the pose of a face and plot them on the output stream on the OpenCV2. So with the head pose, we can have some application of our project. So here is an art interactive installation based on head pose estimation, and we can see from the left picture that there are 8 clocks on the wall, and all the 8 clocks were connected to Arduinos, and there are 4 Arduinos connected with these clocks. And when people are standing in front of the camera and looking to a certain clock, that clock will start to rotate. And so here we use Arduino to control the servos attached on the backside of the clocks, and we use PY serial module for serial communication. And here should be a video, a demonstrating video, but we don't have enough time for that, so we will show our video on Thursday during the face-to-face presentation. And that's all for our project. And here is some reference. And that's all. Thank you.
Thank you.